Next, we're going to have up Dr. Gershwin come up. Dr. Gershwin is a distinguished professor at a professor of medicine at UC Davis. He's done quite a bit in antimicrobial antibody test for patients with PBC, expert in diagnosis and treatment of other autoimmune diseases, and continuously funded by the NIH for over 50 years. So you'll have all this information available to you, but we want to thank Dr. Gershwin for coming up and speaking more to us.
Well, as always, I appreciate being here. I'm not sure what year it was when I went to the first meeting, but I will say at the first meeting, I wasn't stiff when I walked up the stairs, which I just was now. And I'm the guy who's really complicated, and I'm sorry, but I'm going to really do my best to kind of bring you up to date. And I'll give my conclusion before I start, which is that the advances that have been made in understanding PBC have been so incredible that they're enormously more than I could have ever hoped for whenever it was when I came to the first meeting, which I think was probably at least 25 years ago, but who knows. Anyhow, let's see how we're going to do this. I know they had some issues with my slides. Do I have anything to use to point? I got that part. But how about pointing? Any pointer? Anywhere? A pointer? It's always nice to point. It's just, we all grew up watching, I grew up watching Sesame Street. Actually, I didn't. My kids grew up watching Sesame Street, but yeah, that'll help. Thank you. And that's just the point, right?
Yes, sir.
Okay, let me see if I can get it to work. Well, it's kind of a small pointer, but my vision is not as good as it once was either. So look, can we go back? Go back one slide. Why me? Why did I get PBC? All of us ask that question. We ask it whether you have PBC or heart disease or cancer or anything else. And, the answer always is, well, you inherited something. And you must have been exposed to something. What we call both an inheritable and an environmental insult. And all that is true, but it doesn't really answer the why me. And also it doesn't answer a different question, which was, when did it start? Did it start when I got diagnosed? Did it start 20 years ago? And how did it start? Well, we've done research over the years that the PBCers have been enormously helpful for. We did the first study of epidemiology, really anywhere in the world, that was started here by this group. We've developed animal models. We're advancing new therapies. But most importantly, we're trying to get at this issue of why me. Because at the end of the day, let's stop PBC from happening in the first place, right? Can I have the next slide? The next slide. There we go. So let's call autoimmunity the long and the latent road. What I mean by the long and the latent road is here you are on the left at the beginning of the road, and all along the way things happen in your life until ultimately you have a diagnosis. How long is that road? If it's an upper respiratory infection, the road can be measured in hours to a week, week and a half. If it's a disease like RA, like rheumatoid arthritis, it can be measured in 5 or 10 or even 15 years. Meaning in patients who have RA, rheumatoid arthritis, who are diagnosed at the end there, the pointer, there we go. They actually had the pathogenic autoantibodies found in their blood 15 years earlier. But they're healthy and they're unaware of it. How about patients with PBC? Let's try and discuss that. Can I have the next slide? So, why is there so much autoimmunity? You know, most people think autoimmunity is actually uncommon, but it's not. Autoimmunity can affect up to 11% of the population. Hashimoto's, thyroiditis, type 1 diabetes, all very common. It affects, in this slide, 5% of the general population. It gets higher as we get older. Get on the next slide. 80% are female. Next slide. Oops. My slides are, you know, they kind of evolve into each other. I shouldn't make such fancy slides. And the reason, the multiple reasons why women, oops, don't do that. Go back. There we go. The reason why women seem to develop autoimmunity has to do perhaps with estrogens, their immune system, they're built to survive, they're stronger. But at the end of the day, we don't really know the answer, most likely because there are multiple answers. But I will share one piece of data which is often forgotten. We all say, well, it must be estrogens. And estrogens obviously have a role. But here's the piece of information I'll share with you, which I think is really fascinating. We have about, how many genes? 20,000 genes, actually a few more thousand than that. 50% of all the genetic elements in humans are in part controlled by estrogens. Just think of that. 50% of all the genes in your body are influenced in some part or another by estrogens. Can I have the next slide? So let's talk about this, what I mean by latency time, which is there's a prolonged interval between whatever precipitates it and the appearance of clinical disease. So, without even having to read all this slide, on the left it says a variety of insults. Suppose PBC is caused by eating a very bad apple in 1980, and you get PBC in the year 2022. How would you ever know? We do know you don't find PBC really in any significance in any pediatric group, but that's also true of MS and some other autoimmune diseases also. But along the way, there are various biomarkers. One biomarker is called the anti-mitochondrial antibody, and I'll talk about it. It's how I got started in PBC in the 1980s. And we can find a positive AMA in people that do not have PBC for years and years before the disease ever appears. And if they truly have a positive AMA with the right test, I can almost guarantee they will get PBC. So what causes that AMA for years before you get sick? And what happens when you go from the asymptomatic, I'm healthy, but I happen to have a positive AMA, to someone who suddenly has an elevated alk phos? And let's try and explore that. Can I have the next slide? It's really the latency. So here's my warning. This won't be easy to follow, but I'll do my best. And I'll hang out in the back for any questions you may have. I'm not going to try and make this simple. In fact, of some interest is a portion of this talk was given at the University of North Carolina, which is just a few miles away. And the reason I mention it is I gave this talk at the end of February of 2020, just before the pandemic hit the fan. And I remember after the talk, sitting around with Dr. Ron Falk, who's the chairman of medicine at UNC, and we both were talking about the pandemic in Italy. And we looked at each other and said, boy, if it happens here, we're really in deep trouble. Oh. Next slide. So, what's the average age for diagnosis? It depends on the disease. RA, typically, 30 to 50. Lupus, 15 to 44. PBC, we say the average age these days is about 40. But actually speaking, we used to consider it a disease of older ladies. Are we diagnosing it earlier now because it's easier to diagnose? Maybe that's a question Dr. Bolus should answer. But I remember at the first meeting I went to, the average age was a lot older than I see looking out here. And I certainly know that's true of the studies that have been done by my colleague Pietro Invernizzi in the UK. Can I have the next slide? And by the way, although I don't think I can prove it, I think PBC has gotten more mild over the years. And yeah, certainly the medications have helped a lot. But PBC would not be the only autoimmune disease whose natural history has been altered over the years. In RA, rheumatoid arthritis, disease is much different than it was even in 1960, 1970. Certainly a genetic predisposition accounts for about a third of all the autoimmune diseases, whether it's lupus or rheumatoid arthritis or PBC. So what are the environmental factors or factors? Because one thing we're beginning to think about autoimmune disease is that there are a series of stochastic or random events that occur in each of us with a genetic predisposition. And as we're exposed to those stochastic events, one at a time, we push ourselves closer and closer to developing the clinical disease. So you have the autoantibody, maybe it's a viral infection, maybe it's vitamin D deficiency, maybe it's multiple other events within the environment. And ultimately, the clone that produces the disease becomes more important. Maybe it's other infections, and you go from preclinical to clinical. Next slide. The history. These are slides given to me by Pietro Invernizzi. I somehow couldn't manage to put his name on the slides, so I'll show it here. And I like these slides because they talk about the history of PBC. First slide. Well, the first case report of PBC was in 1851. Well, that was obviously before my time. But on the other hand, I have to tell you the first case report, or what we think the first case report of systemic lupus was in about the 4th or 5th century. We have cases of RA back in the 1500s. There's a disease called ankylosing spondylitis, and it's described certainly by around the year 12 or 1300. Now, and by the way, you don't just, they weren't just described by doctors. They were discussed as characters in fiction. They're in oil paintings hung in the Vatican, where you can see people with deformed hands. Look, they have RA. There's cases of women with a malar flush, sorry, who we think had systemic lupus way back in paintings from the year 1100, 1200. Actually, I'm not sure exactly. How was it that PBC really wasn't described that well? Well, maybe it's because it's a female disease, and maybe people didn't pay that much interest to women back then. Or perhaps it's because there was a disease of older women. Or they didn't have the test, they didn't survive long enough, all sorts of reasons. But actually speaking, the real beginning of the modern era of PBC really wasn't until 1965, when the anti-mitochondrial antibody was detected by immunofluorescence. 1987 is when I cloned the antigen. UDCA was approved about 18 years later. I can't read the slides with my eyeglasses here. And then, of course, we changed the name. Who were the people involved? Just for fun. Early on, they were, next slide. Next slide. Early on, they were clearly from the UK. But probably the most important figure in the development of understanding of PBC was an Australian named Ian Mackay. Can I have the next slide? And here's Ian on the right. It's a younger version of me. Ian was a young man in 1965, and he was the one that described the anti-mitochondrial antibody. And he really is the godfather of PBC, and the one who I think has advanced more about autoimmune liver disease than anybody. He passed away about a year and a half ago, incidentally. In 1987, I moved to Australia to spend 6 months working with Ian. The work went so well that I stayed for 18 months, and it wasn't until I got a fax from the university that said, your sabbatical's over. If you don't come home soon, you're going to lose your health insurance. But Ian and I managed to clone the autoantigen PDC, and I think that really did help as a platform to beginning to understand the molecular biology of PBC. And that's what I'll try and talk about now. Next slide. So, humans. Standing up here, there's just me. What's in my gut? There are more bugs in my gut than I have cells in my body. So who owns me? Okay, is it me or is it all the bugs? And we certainly know that a theory called the hygiene hypothesis, which was advanced by a couple of people, including Jean-Francois Bach in France, was that we are much too clean. We give antibiotics much too soon. That if your baby's pacifier falls on the floor, stick it back in the kid's mouth. Being exposed to dirt is good for you. Growing up on a farm is healthy. And he was right. He and others were right, that there's more autoimmune disease where you are too clean. There's more allergies and asthma when you're too clean. Is there a specific bug in the gut that's involved in the development of PBC? We think there is. We think it might be more than one bug, and we'll explain why. Next slide. So is there a flaw or weakness? The numbers are on their side. Let's try and exploit it. Next slide. We'll skip that. Next slide. Okay, so what produces autoimmunity? I mean, if I gave a lecture to a group of academics, what are the mechanisms by which it starts? Well, by far the most commonly prescribed is the first one, a molecular imitation. What does that mean? It means a guy goes into a bar and somebody doesn't like him and he beats him up. And the guy goes home and he's all black and blue, and he gets 6 of his big friends and they go back to the bar. And they see a guy that looks just like him, but it's not him. But they beat him up anyway. The point is that you may have a molecule in your body that looks like something on the outside. Your body reacts to that something on the outside, and it turns and attacks yourself. We know from the COVID vaccines, which are outstanding vaccines, obviously, but we do know, at least in the Johnson & Johnson vaccine, there can be autoimmune reactivity, particularly in the heart, and there's an interesting form involving clotting. And that seems to occur, although the mechanism is still not clear, that there is some form of attack against the COVID vaccine that cross-reacts with yourself. It's a pretty simple thing to understand. The problem gets back to the bad apple. Suppose the mimic or the cross-reactivity, the person who looks alike, is someone you met 20 years ago. How would you ever know that what happened 20 years ago is the mimic that starts your disease now? It's really hard. It's really difficult. And with the exception of acute rheumatic fever, which is a disease caused by reaction to a bug, Streptococcus, that then turns on your heart, with that single exception, it's been really hard to prove in humans. It doesn't mean it's not true. It certainly is true, but it makes it more difficult. Other theories, there's one called self-antigen modification and epitope spreading. Those are awfully big words. Well, I think I've got a slide to explain that because it's a theory that I think is very important here. But I'll explain it now, and then I think I'm going to show it as a picture. But essentially, PDCE2, which is the enzyme that you react to if you have PBC, has a swinging arm in this big molecule. And that arm contains lipoic acid, which is a chemical. And that arm opens and closes, and it captures electrons. And we all need to have it. But it's in the bile. What's in the bile? All the poisons and toxins of the body. In fact, does anybody still eat any chopped liver in this room? I wouldn't recommend it. Unfortunately, I grew up on it, but I didn't feed it to my kids. You're eating garbage when you're eating chopped liver. But the point is, with this lipoic acid, you're exposed to chemicals all the time. And you could easily see how the chemical could attack that PDC, alter it. Your body reacts to it, and then it turns on itself. There's another theory called bystander activation that I'll talk about. And the other two I'll talk about with slides, but not in as much depth. Can I have the next slide? Here's the bystander effect. Bystander effect is one we tend not to think about, but it's one immunologically that's very important. So, EB virus, the virus that causes mononucleosis, has been implicated in just about every autoimmune disease that you think about. But probably not because EB virus itself causes the disease. It's because EB virus gets your immune system all revved up and all amplified. So suppose you already have an antibody, a bad antibody in your blood. Maybe an infection like EBV or some other infections gets your immune system all revved up, all amplified by a whole variety of bystander cells. And that completely alters the natural history, that up until that point, everything was under control, under good regulation. You know, there's lots of examples of that. You get a sore throat, and you get swelling of lymph nodes in your armpits, in your neck, sometimes even elsewhere in your body. But those lymphocytes that are swollen in your armpits, they're not really reacting with the virus in your throat. They're what are called bystander cells, meaning a house catches on fire, and fire trucks from all over the city all arrive. But only one truck is needed for the fire, but there's 18 more trucks there. And those 18 trucks are doing damage. That, I hope that wasn't too hard. Get on the next slide. The next slide. In fact, I already mentioned what molecular mimicry is, and just to remind people who aren't scientists that rheumatic fever, which we hardly see anymore, is caused by infection with a strep bacteria. And those who have a genetic predisposition react with the strep, but the strep also, let me start again, reacts with the strep, but that same reaction also reacts with your heart muscle. Meaning those people with the genetic predisposition have some antigen, some molecule in their heart that looks to the immune system like strep. People have been trying to find a look-alike for PBC for a long time. We think we have some chemicals that we induce PBC in mice, but we'll talk about that. Can I have the next slide? What's really important, that's fine, we're good there. What's really important is that the epidemiology of PBC, what is epidemiology? Study of epidemics. You know, why did this population get sick and this population did not get sick? Why is there more tuberculosis in Philadelphia than there is in New Haven, for example? Well, when epidemiology has been applied to PBC, and that includes the study, the very first American study, in fact, actually the very first worldwide study on PBC that was done by the PBCers, we found that women with PBC tend to have a history of more urinary infections. And that's been reported now and confirmed by the Brits, by the English, and I think by the Japanese as well. Well, what causes urinary infections? We'd like to think it's only E. coli, but actually there are lots of different bugs that can cause urinary infections. And interestingly, and this is work that was done in my lab over a good many years, if you make an antibody against the E. coli, it also reacts with human PDC. And so one theory has been that this urinary infection in the genetically predisposed person is the first of those stochastic events that starts things out. But it's been really, really hard to prove. And so we began to think maybe a little bit more out of the box than usual and ask ourselves, was there a footprint or a fingerprint that was left behind during a urinary infection? Meaning, were there other immune reactions that took place that we could still find evidence of, even if it was 20 years later? So we began to collaborate maybe about 4 or 5 years ago with a group of E. coli experts. People that study E. coli have nothing to do with PBC. And what they did is they started to make different structures, so to speak, on the bottom right, different kind of species of E. coli. And they began to make them in loops. They began to make them the way the body would really see things. Because remember, we don't see things flat. We see things as holograms. We see them three-dimensionally. And that's what they did. And we found that if we got sera from women, and I think we only had women in this study, during the earliest stages of their disease, they were more likely to show IgM antibodies, which are the first antibody against those unique species of E. coli. And so, while it isn't 100% proof, I'm convinced that at least one way that PBC starts is some form of what we call gram-negative exposure. It may not even have to be an infection, but an exposure that begins to set the stage for the development of the anti-mitochondrial response. Can I have the next slide? Sort of the hypothetical explanation for all of that is that in the middle we have what's called the microbiome of the gut. And that microbiome is the second largest immune organ in the body. The first largest immune organ in the body is the skin. The gut is the second largest. Although if you're a gastroenterologist like Dr. Bolus, he'll argue that the gut is larger than the skin, but I would disagree. But even so, they're both really big. And it's a way by which you can bring antigens into the liver, into the bile. Why do we have a liver in the first place? To metabolize bananas and nuts. Liver developed an evolution for metabolism. But metabolism has gotten a lot more complicated with all the chemicals, all the foods, and everything we're exposed to. So one of the things we did, and you'll see the word xenobiotic in the middle there, is we took chemicals and that seemed to be involved in the antigen PBC, and we went over to meet some organic chemists. Interestingly enough, initially the chemists that worked with us were down at the Lawrence Livermore Lab. Lawrence Livermore Lab, of course, is where they started to make the A-bomb, the atomic bomb once upon a time. But at the time, the world was much safer than it is now. This was probably in the early 90s, the mid-90s. And these guys didn't have any work to do because the Soviets weren't doing anything. And they were looking for other projects. And their job as chemists was to figure out where people were storing radioactivity all over the world, by the way. And so we got them involved, we gave them the antigen, and we said, can you find any chemicals in the environment that would look like this? And after years of work, going through encyclopedias of antigens, they did come up with some chemicals. And we immunized mice with these chemicals, and the mice seemed to get a PBC-like disease. And some of you know we've published a dozen papers on this. It's been well funded by NIH. But one of the things about these mice is they didn't get any fibrosis. They seemed to get an injury, they had their mitochondrial response, but they didn't go any further. And that was a real disappointment to a lot of people. But even so, it was an example that E. coli could induce a PBC-like disease, but also certain chemicals could induce a PBC-like disease. One of those chemicals, by the way, is called octinoic acid. And it's so prevalent that it's found everywhere. I mean, it's in food, preservatives. It's in probably 80% of the things on grocery shelves. It's not even listed as an ingredient sometimes because it's so small that it just gets in there. Can I have the next slide? I put this slide in because someone asked about other things. And I'm always asked about, when I talk about E. coli and chemicals and things that we think induce PBC, what about the questions that everyday people ask? For example, anxiety or lack of sleep, vitamin deficiency, other medications, smoking, alcohol, lack of exercise, hormones, hygiene, age, many of my other diseases. And the reality is they probably all have, to some degree, an effect on our health. But the exception of vitamin D, and with the exception of hormones, there really isn't any significant evidence that they really induce an autoimmune disease. Soldiers going into battle don't get a higher incidence of getting lupus, for example. And there's lots of other examples as well. But they certainly can affect your general health, and then, of course, can affect your underlying autoimmune disease. Vitamin D is interesting immunologically because it's very important to maintain immune homeostasis. The immune system undergoes better regulation, it functions well under good levels of vitamin D, and you get vitamin D from the sun and from your diet, of course. But if you live in Chicago and you're spending most of your year indoors, you're not getting much sun. Okay, if you live in California, where it hasn't rained in any significant amount in at least a couple of years, you get a lot of sun. Can I have the next slide? How about things you eat? You know, I always tell people eat a healthy diet, which is basically, don't eat fatty foods, reduce your meat consumption, eat good leafy vegetables. Is there any evidence that it really helps? Well, there's evidence that it may help your heart. Whether or not it helps an autoimmune disease, I don't think so. Next slide. I said amongst the mechanisms of bystander activation and molecular mimicry and antigen modification, I would also include cancer immunotherapy and what the various new drugs are. Now, I don't know if you know about what's called PD-1, all the checkpoint inhibitors, but there are now a number of drugs which are given to people that have cancer that are designed to unleash the immune system to attack the cancer. And it works, thankfully, and there's a lot of research going on. But what happens when you unleash the immune system? Well, you may get too much unleashing. And in fact, on the right is a list of autoimmune diseases that have occurred in people with cancer that get these various drugs. And it reminds us that immune regulation is so important. It's one reason why one of the major advances which we hope will happen in autoimmunity is to improve immune regulation. Because the immune system is like the thermostat in your home. It can't be too cold and it can't be too hot, and it's about as promiscuous as any physiological system in your body. What do I mean by promiscuous? Well, if you live in a big house and you open the window in one bedroom upstairs, it's going to make the whole house get cold. If you overheat a room and it happens to be far from the thermostat, you can also dysregulate the thermostat of the house. And so what happens in autoimmunity is that dysregulation that takes place through what are called T regulatory cells. And in PBC, as in a lot of other autoimmune diseases, we seem to have a deficiency of those T regs. And so hopefully, one way would be to restore that degree of regulation. And the fact that autoimmunity is taking place when you unleash it with these various drugs is evidence that there is that balance taking place. Next slide. So, the chicken or the egg? The chicken, I put these in, Carol asked me to put these in. The chicken or the egg? So, you know, there's a couple of interesting arguments that go on in academics in PBC. One argument is it's all due to your immune system. You get autoantibodies, and especially you get abnormalities of your cytotoxic T cell populations. And I really haven't got into that much. I know others will, I'm sure. But really what's working, attacking your liver mostly are the T cells and cells related to the T cells. And the antibodies are an interesting bystander that goes along. They may also be functional, but the T cells are really very critical here. But the other half of that argument is made by groups in Europe. And they argue it's the bile, that the bile is inflammatory, and that the bile itself perpetuates the disease. And when PBC comes back after liver transplantation, it may be the inflammation of the bile which is so important. And it's a tough question to answer. Because on the one hand, we want to develop drugs for the immune system. On the other hand, you want to develop drugs for the bile, if that's true. We already have some drugs for bile. Dr. Bowles has already discussed them. And so we call that the chicken or the egg. Is it the immune system or is it the bile? And we made a very interesting observation. And this was actually made by a former postdoc of mine in Japan. And here's what he did. Can I have the next slide? I know this is going to get complicated, but I'm going to really make it easy. Next slide. Okay, here's what he did. He took one of the models that we've developed to develop PBC in mice. And by the way, our PBC mice are now used all over the world. We have given these mice without any contracts or requirements to anyone who's ever asked for them. The same with all the clones we've ever made. Big companies, small companies, we're happy to share. We want to share. We want to cure like you want to cure. I used to say I wouldn't stop working until I retired. It's getting harder. But here's what he did. The mouse has its own bile system, different bile salts than humans do. He took a mouse that had been genetically engineered, actually only partially engineered based on the resources they had. And he took this partially engineered mouse that had human bile. And he exposed it to one of the chemicals that I believe can cause PBC. But in my hands, it never progressed. The mice would get AMAs, but they wouldn't get fibrosed. If he immunized that with a mouse with human bile, they get significant fibrosis, inflammation. It's much too small to see. Get on the next slide, it might be bigger. And they get elevation of a variety of genes that are involved in the inflammatory response. And, next slide. The degree of difference over time between the control mice and the mice who get the chemical and have the human bile is just extraordinary. I know these are too small to see, and these obviously are from a scientific publication that's being submitted. But here's the point of this. The point is that it's not the chicken or the egg. You're not going to get PBC without a disrupted immune system. But the perpetuation of the disease is in part secondary to altered bile, to the inflammation of the bile. Which means that if we are to develop new drugs to impact the immune system, giving them early is going to be really important. It also means that if you have a liver transplant or you have advanced disease, that we shouldn't forget the absolute necessity to manage the inflammatory components of the bile salts. So what's happening now? We found that a mouse that was much better than the one that was made in Japan had actually been made in Europe, genetically engineered in Europe I think about 15 years ago. I keep saying 20, but I think it's 15. But unfortunately, it was done by people who studied bile and chemicals, and they didn't do anything with them. But they gave frozen embryos away to a company like Jackson Lab. It's a different company, but it's related. And they're frozen away. And there are 4 embryos. And so we've made arrangements to get those 4 embryos. They're being unfrozen for us. They're going to be shipped. We're going to raise the line, and we're going to be able to prove, we hope, the chicken and the egg, and how to treat, and at what stage to treat. Because at the end of the day, if personalized medicine meaning medicine designed for you means anything, it's going to be a disease like PBC, where patient A may not get the same therapy as patient B, depending on where they are at the stage of their disease. And with the emphasis of treating early. Can I have the next slide? I think we'll skip all the genetics we did. Next slide. Keep going. And so tissue inflammation results in the production of numerous reactive oxygens. And so it's the inflammation that actually produces the destruction. And that's where the problem with the chicken and the egg comes from. Because the inflammation doesn't care whether it's from the bile or the bile salts or from the immune system. Inflammation is harmful. And that's why preventing that from happening is going to be the key to prevent the progression of this disease. And I think the next one is my last slide. Oh, skip this one. We don't need to talk about this. And so the conclusion, I believe there are going to be a variety of insults and exposures over time that lead to PBC. There's not going to be just one. There obviously is a genetic susceptibility, but that susceptibility is not going to be one gene. It's going to involve multiple genes. The concordance of PBC and identical twins is fairly high. It's a study we did here. It was around 50 or 60%. Obviously, it was on a very small number. The concordance within a family is much less. In our hands, it's 1 to 2%, which means you shouldn't run out and be all worried about your kids. Obviously, we do in any family history of autoimmune disease, but the risk is low. Onset of symptoms comes years before that latency period until ultimately you have clinical disease. But that latency time is not a quiet or an inactive time. Things are happening in your immune system all along the way, which means when high throughput the diagnostics become introduced to the market, we may be able to diagnose people for years before they would have been diagnosed anyway. High throughput is something like this. There will be a way to measure 20, 40, 50, 100 autoantibodies all at once on a small amount of blood for a not very expensive price. Probably, I bet, before the decade is out. And it's in everyone's interest to diagnose early, because early diagnosis leads to early treatment. Let me give you an analysis about price. The Human Genome Project. That DNA was sequenced when Ronald Reagan was president. Any idea how much it cost? Over $1 billion. Guess how much now to sequence the same amount of material? It's about $1,400. And frankly, it's going to be probably no more than $200 by the end of the decade. That's how fast the technology is moving. I mean, I've always predicted when a baby is born in America, in the future, they will receive on birth, as they already do, their social security number. They'll get a cell phone number, which will be their number for the rest of their life, and they'll get their DNA sequenced, which will be a lot cheaper than the heel stick they do these days for babies. You wait and see. It's going to happen. But you know, I think I do have one more slide. Maybe I'm wrong. That's right. And that's the future for treatment. And I think the future of treatment is going to be more than one agent. But I really believe we're moving into the age of drugs that will modulate and improve the immune system. And I really look forward to those happening. And I'll end with the anecdote that when I started this work, I couldn't even get Big Pharma to return my phone calls. And now we have all these new young companies with new molecules and new technologies. And I really think this is going to happen. You guys are going to get a cure before I do retire finally. Thank you very much.
Thank you, Dr. Gershwin. And we have a few questions that would be interesting. And I think we have some extra time for the next portion, so we'd like to get to these. A couple questions around the genetics and specifically around race. Why, I mean, as you look in the audience, it's not really diverse. We see a lot of white women and not much black and brown women. What is that about?
So it's an interesting question. For one thing, the incidence of PBC in every ethnic group is about the same, with the exception of African Americans, which seem to have a much lower incidence of PBC. Yet African Americans get a lot more lupus and a lot more RA, but they don't seem to get PBC. We don't know why. We do know when you look at the the genes involved. There's no obvious difference to explain that difference. There are differences in that explain the incidences of PBC in countries like India, for example, and that is PBC in India is relatively uncommon, but we have people of Indian descent living in the US and the UK that get PBC. And that probably has to do with the hygiene hypothesis and being dirty or, or growing up with large families on farms is healthier than our form of existence. But that's not the case for African Americans, and it is a mystery.
Great, thank you for that. And another question around, being that it's autoimmune disease, as far as diet and kind of affecting, not only your general gut health, but also this aspect of autoimmune diseases. What's your thoughts on that and influencing?
So, one way to treat lupus is starvation in mice, at least. I'm not recommending that, by the way, as a therapy. And, there are risk factors of being overweight and there's, metabolic dysfunction and so forth. But overall, there's no single factor. I do sort of warn people away from dietary supplements. So one popular dietary supplement used to be lipoic acid. Many women at some of these meetings were taking lipoic acid. And I was publishing on lipoic acid because that's part of the autoantigen that you react to. And I was invited to a meeting on lipoic acid. And as soon as they found out that I was saying you shouldn't take it, I got uninvited from this meeting. But I don't think people should take lipoic acid. And I'm always a little cautious about dietary supplements because you never really know what's in the box. And there's no regulations. So Gary Henderson, who is a pharmacologist once upon a time at UC Davis, did a study on it was either echinacea or ginseng. I think it was ginseng. And he went out to the co-op in Davis and Sacramento and he bought about a dozen boxes of ginseng. And he measured how much ginseng was in the box. And it turned out, I think, there were 2 or 3 that only had starch. There was no ginseng at all. And there were a few others that had some in there, but it was a fraction of what they claimed. So, buyer beware. Most of it is just not what you read.
Great. And then we have another question around for AMA and ANA negative PBC. How do you explain the PBC origin? Is it still autoimmune, even though they're negative?
Yeah, it's a good question. So, AMA negatives. So, first of all, most hospitals test your AMA by immunofluorescence because that's a very cheap way to do it. If you do it with the recombinant autoantigen, which is the diagnostic test, and by way of transparency, the University of California owns the patent for that test, and I get about $18 a year in royalties on it, and not much more. That is the test. It is diagnostic, and it lowers the number of AMA negative patients to no more than 2.5% to 5%. But there are those that are negative. We have looked at a handful. Shinji Shimoda in my lab looked at a handful of those AMA negative patients, and they still have T cells that react with the same mitochondrial enzyme. And so the analogy that I use is that, there are some patients who get immunized with a hepatitis B vaccine, and they never make a decent hepatitis B antibody. Sometimes you have to immunize them 4 or 5, 6 times. But some of them still have T cells. Whether they're effective or not is another matter. But we think of the AMA response as a multilineage response involving the antibody, which is the test you're referring to, but also involving CD4 and CD8 cells.
Great. And one other last question on pre and probiotics in a diet capacity. Helpful, not helpful?
Really good question. And I have to tell you that we have a $500,000 grant now looking at the effect of giving certain dietary, I don't want to tell you which one it is because you're going to run out run out and buy it, and I don't want you to yet. But a chemical that we think is going to raise butyric acid in the gut and make it anti-inflammatory. We don't think it's going to be a treatment, but we think it might be ancillary. We're hoping it might be ancillary. And if you would like to read about it, interestingly, the work was done by Charles Mackay, who happened to be the oldest son of Ian Mackay, who's himself a professor of microbiology and immunology in Australia. And that's Mackay, and first name is Charles.
Great.
And we're using his diet on some of our animal models. But it is way too early to know.
Awesome. Thank you for that. I think Carol has something for you as well. Yeah.
I was trying to figure out if I was going to have to get really close to Dr. Gershwin's mic to talk to you. So randomly, Dr. Gershwin will send me a text. And about a week and a half ago, he sent me a text, and he started talking about the mice he was looking for the chicken and the egg project, as he's now, I guess, calling it. And he said, do you know anybody? He said, I'd really like to get this started, and I got to find the funding. And I said, huh. So I'm very pleased to give Dr. Gershwin the money he needed to buy those 4 mice. And this is from the donations that the PBCers have made over the past year. And it is my hope we are going to start funding, collecting funds for this. And my hope and dream is that we will be able to fund that entire project from beginning to end, because that is one of the most hopeful for our dream of finding the cure or how to keep people from going farther. So thank you, all of you, for the donations you made, and thank him for his dedication to PBC research.
And this is really for all of us in this room. So thank you again.
Okay. I think that's it.